Okay, so welcome back to our channel. So now we are going to be solving an example which involves the Jacobi. So here the first part, they are saying why is it possible to guarantee the convergence of the Jacobi method. So we can first extract the matrix A. So now after extracting our matrix A, so we can use which theorem? We can pause and think about it. We have used this theorem before, so we shall redefine it. So if we are using this theorem, if A is strictly diagonally dominant by the rows, the Jacobian Gauss-Seidel methods are convergent. Okay, so how do we go about this? So meaning we have to check for every row. So for row 1, strictly diagonal dominant, we have talked about this. Go to the magnitude of the diagonal element must be greater than the sum of all the other elements in the row. So for row 1 it holds, for row 2, is it greater? Excluding the row element. It works for row 2, does it work for row 3? The diagonal element is still greater. Does it work for row 4? The diagonal element is still greater. Something like that. So meaning, using this theorem, I can conclude that the Jacobi method converges. So it does do converge. Okay, so we can move to our next part. So how can we use the Jacobi? The Jacobi method to solve a linear system presented in the previous question. That question. Presented above. That question. So when using the Jacobi method, we shall use this. The entries before, you meet the diagonal element and the entries after the diagonal element in the same row, in the row I. Okay, so from our method we have matrix A. So to use the method we need the A, we need the B, we need the X naught, the initial value. So we come for K equals to 0. So by X1, that is going to be given by, what is my B1? It's here, 2 minus, now I will use these ones, times their initial values. So this is 1 times the initial value, it's a 0, minus 0 times 0 minus negative 1 times 0. Something like this, then times 1 out of 4. So it is the pivot. So that's how we get 1 out of, is it a half here? So we do the same thing for X2. For the Jacobi it's very easy, since we don't need to use like the new value that we get here, just like in the Gauss-Seidel, but here you use strictly X naught. So now I'm here, so I will take this and that. So this is 4. Is it 4? No, it's negative 2. So this is negative 2 minus negative 2 minus 2 minus negative 1, only that it's times 0, minus negative 1, only that it's times 0. These ones you get corresponding on the column. Then this is also 1 out of 4. So we get negative 1/4. then x3, it's negative 2 minus, now here I use this, ignore that and that, but they are still zeros. This is also 1 over 4, so this is equal to negative a half also. Then my x for 2, x for 1, we are just on the first step. X for 1, this is equal to, this is 2, this 2 here minus 2 minus negative 1, so I'm using this. Negative 1 times 0, negative 1 times 0, yeah, this has really been boring. This is also 1 out of 4, so we have a half. So we see that my x1 is a half, negative a half, negative a half, this is a half also. Transpose. So, okay, then we continue. Then we continue to the next step, step 2. Okay, now for step 2, this is where k equals to 2. K equals to 1, I mean. So yeah, now this is 2, now 1. So the first one is still 2 minus, take this and that and that. This is 1 times the initial value, which is a half. Then this is 0 times the corresponding initial value, which is negative half. Then I take negative 1 times the corresponding initial value, which is a half. I don't know if you have observed that the corresponding initial value here is negative a half. So this is negative a half. Then times 1 over 4. So we get 3 out of 4. Then we do for x2. For x2, it's going to be, I use this and 0. So the first bit is negative 2. It's here. Negative 2 minus, this is negative 1. The corresponding value, initial value is a half, minus negative 1, the corresponding initial value is negative a half, minus 0, the corresponding initial value is a half. This is also 1 out of the element in the diagonal with respect to that row. Okay, so this is going to be negative 2. So we get negative a half, then we go to x3. Equals to, now I use this, that, ignore this, use this, ignore that. So this is negative 2 minus, this is 0 times the corresponding initial value, 1 times the corresponding initial value, negative 1 times the corresponding initial value. So what do we get? This is also 1 out of 4. So x for this one, this is 2 minus this, that. Negative 1 times the initial value, which is a half, minus negative 1 times negative a half. Just that, this is still 1 over 4. So this is our solution. So we can write it in that form. So that's how we can use the Jacobi method. However, we can also use the Jacobi over relaxation method in the same way, and it's it. So for the Jacobi relaxation method, Yeah, we can use the same iteration method. However, you multiply here with omega, the relaxation, plus 1 minus omega times xi. Okay. Yeah, this brings in the initial value of the diagonal. So omega is given, then the rest of the things are done in the same way. Then you choose this from the initial values. So that's it basically. So yeah, we meet in another video. Wish you the best. Thank you. Please subscribe, like. Thank you.